Okay, we're just about to start. I'm going to give you some front matter, and while I do that, I do recommend that you download a copy of the slides at one of those URLs. I've also just pasted it into the Gitter room. That's because there's going to be some code, and if you have questions, it might be useful to be able to refer to previous slides, just to check on things that I've already talked about. But with that said, I think we can get started. So we're going to be talking about opaque types or coercible new types in Scala today. This is a particular pattern using long-standing features in the Scala language. This is not new Scala features. You could do that. I'm pretty sure you could do this in Scala 2.9. It's even possible that you might have been able to do it before 2.9. I don't know anything about Scala before 2.9. But it has a pretty broad range of use cases. I think in Scala Z8 we use them in 3 different ways for entirely different purposes. But I'm going to show you the general technique and how you can adapt it to whatever practical needs that you have in your applications. So I like types. I write a lot about types on the Type Level Scala blog and on my own blog, Failed Experiments. I've been using Scala and Scala Z for almost exactly the same time and been contributing to Scala Z for almost as long. It's a lot of fun. You should try it sometime. Currently, I'm working at Digital Asset. We are one of those blockchain companies that they mentioned yesterday, that John mentioned yesterday. We have a typed, purely functional smart contract language implemented in a split of Scala and Haskell. If that sounds interesting, then maybe you'd like to join us. And I've got the URLs up there. So I hope everyone who wanted to has a copy of the slides, because now we're going to look at some coercible new types. So the goal is something like this. This is a type alias. So if you just write this in your program, it means label equals string everywhere. It doesn't, you can write label in as many of your argument ascriptions as you want. It's still going to let you just pass strings. So it might produce some documentation convenience by itself, but it's not going to produce any additional type safety. But additional type safety is desirable, or if it's not, then just go write JavaScript or something. So an opaque type, or an opaque type alias, it's present in several languages as a first-class construct. Like an alias, the runtime representation is exactly the same. There's no object wrapper or class wrapper that you get if you try and do object-oriented abstraction. You have a question? Okay, sorry. So it's like an alias in that way. Unlike an alias, it's treated as distinct at compile time. So we have same at runtime, but distinct at compile time, which is kind of the opposite of what you're used to. A little bit, but that's pure type level abstraction, using just the type system to enforce an abstraction that doesn't have any sort of reification at runtime. But we want one more property, and this is where something like any Vowel classes falls down. We want it to be coercible. That means that not only can we take individual values and take them back and forth across the opaque type barrier, we can also take data structures containing them and take them back and forth. We can even take functions that operate on string, in this example, and turn them into functions that operate on label with no runtime wrapping or unwrapping happening. So coercibility is very important to having a low or zero cost abstraction. And I got the idea for how to do it from a really old Scala user message by Julian Michael. Like many of the very interesting messages to Scala user, this one went with no replies because it was too sophisticated to get a lot of replies. All right, so hi all, I might be exploring a well-worn field. Well, yes, if you're talking about OCaml or SML, but not at all in Scala at the time. But the key point here is, he says, it seems to me that you can use abstract types to do opaque sealing to make a type alias, etc., etc. So that's exactly what we're going to do. We're going to borrow the technique from the ML family of languages to create opaque types. And because we're borrowing it from ML, and the things that you write down have a very similar structure to what you write in ML, we're going to use ML's names for these things. There are 3 elements to a opaque type definition. So the first thing is the signature. So what's up there now? The signature declares what is publicly visible about your opaque type. So in this case, the opaque type is label. It's the label member. Because we want it to be opaque, we can't say anything about what label is here in the signature. We just have to say there's a type label. Specifically, we say there's a type label, and we have some primitive functions that we can use to work with that type. We don't supply a way to construct a label, like to use new or anything like that. We don't supply a null bound that would let us widen the null pointer into a label. We just say there's a type label, you don't know what it is, and here are 2 functions that you can use to work with it. So far, we don't really have anything more impressive than an AnyVal subclass. The second part is the structure. So we have the signature, which declared the public interface, and we have the structure, which declares a private implementation. So we write label equals string in the structure. Now that fact is visible within the structure and only within the structure. We need to use that fact to implement our 2 primitive functions, apply and unwrap. In this context, label does equal string, and therefore both of these functions can just return the argument. That is, apply takes a string, it has to return a label. Well, label is string, so we can just return the string. Same thing with unwrap. Both of these functions have the same exact signature in this context. They are both string-to-string functions or label-to-label functions. They mean the same thing. There's a third element, though. And this is what we need to really make this convenient. This is what everything we've seen so far can more or less be done in Java. This is the part that you really need Scala-specific features to help you out. This is the Vowel. You have a globally accessible Vowel, maybe it's within a companion object or something like that. And when you create your structure, you bind it to that Vowel, and you ascribe it with the name of the signature. So our signature was called label module. We use new label module to provide the structure, and then we assign that structure to a Vowel, which is ascribed with the signature name. And that's what makes it opaque. Because Vowel instance is just a label module. We don't know anything about what's in the structure based on that declaration. We just know that it's a valid instance of the signature. So that's it. You could do this even before any Vowel subclasses existed to get wrapper-free new types. Just to prove that it's a new type, we can go ahead and try it out. So this is a globally bound existential type. And the way you can think about that, if that sounds completely weird, is that you can imagine the whole rest of your program encased in this big function, and it has these type parameters. So it's like a type parameter to your whole program, except inside the structure. The structure knows what that type parameter's value is going to be, but the whole rest of your program has to deal with it generically. And so we use the same mechanism that's used to enforce type parameterized abstraction to enforce this kind of globally bound existential abstraction as well. So even though label is really string, if we try and call a string a label, we get a type error. This is a compile time type error. Same thing if we take a label and we try and treat it as a string. We also get a type error for that. As far as the type system knows, there's no relationship between these types. It's an opaque type. But we're still missing the coercibility aspect. Oh. So this might be useful to you. You know, no one likes null, right? If you like null, then maybe this isn't the talk for you. But we didn't say anything about what label is. In particular, we didn't say that it's a supertype of the null type. And that means that we can successfully enforce that you can't just say null as a label. That might be good enough to make this a worthwhile technique, setting aside all the coercibility stuff, you know, unless you've never experienced any misery from nulls at runtime, which I don't believe you. There are other weird behaviors that come from it being existential. In this case, I've sort of copied the module. I've taken the same structure from the first vowel binding, and I've put it in a different vowel binding, and then I use the signature to ascribe it again, :label module. So I've copied the vowel, and because of that, I've copied the type. So there's still just one structure underneath, right? But Scala will actually treat instance.label, our original opaque type, and instance2.label, our new one, as independent opaque types. So you can use this to create a whole bunch of opaque types that are unrelated if you need them. So everything so far has been pretty much a design pattern. The rest of this talk is just going to be variations on that pattern. So you can refer to these slides if you want to implement your own new types. For example, if you don't want to use a library, or you need to use one of the variations I'm going to show you. There are just two things that you have to remember. First, everything in the signature is public. Everything that's in the structure is private. If you put something in the signature about what your type is, that is going to be known. That is exposed through the abstraction layer. On the contrary, if you write a function and only put it in the structure, that can be very tempting. You might forget to copy the signature into the function signature into the module signature. But if you put the function there, it's not going to be globally visible. And you might be putting a function that's absolutely essential to working with your type. If you just put it in the structure, it's not going to be usable to outside code. It's not as serious a problem as accidentally making something public that should not be. You have a question?
By structure, you mean instantly?
By structure, the question was about what I meant by structure. Yeah. By structure, I meant the second thing, the anonymous new label module here. In the rest of this talk, when I say signature, I always mean this first thing. And when I say structure, I always mean this second thing. These terms come from ML, which is why they're useful, because you can refer to ML techniques and import them into Scala for working with these. Because in ML, they do this kind of thing for breakfast. They don't need an advanced Scala talk to work on these things. So our second rule is always ascribe the vowel. You always have to say vowel, whatever you want, : name of the signature. If you don't do that, you're going to break the abstraction, because that type label equals string, or what have you, is going to be exposed in the vowel. It's part of the inferred type for that structure. So you have to hide that part of the inferred type by using the ascription. Never forget that part. I'm going to show you a little bit more later about exactly what's happening when you use that ascription. So hold on to that. So I mentioned that we're missing the coercibility part, right? Now we want to include the coercibility part. So here's a simple kind of coercion. If label equals string, we should be able to take a list of string and just turn it into a list of label without mapping over the list, right? Because it just is. And we're only using the new type opacity for convenience. We're trying to get the type system to help us. We don't want to, at the same time, turn around and tell us, well, you have to write this map call that's going to be completely useless and does nothing, you know. So instead, we can add a function like this, wrap list, to our signature. We can declare it in the signature. We can implement it just like this in the structure. And why does this work? Because in the structure, string equals label. Therefore, this is a function that takes a list of string and returns a list of string. And implementing that is beginner level Scala, right? I demonstrate that it just works here. If I take a list of strings, I can pass it to this wrap list, and it produces a list of label. And you might notice from that toString output that there's nothing around it, because it's a pure type level abstraction. There's no runtime layer for this label. But what about other things? How many functions of this kind do you want to write? Like, not just lists. I mentioned that we wanted to coerce functions too. We want to be able to coerce pretty much anything. Anything that has strings in it and turn it into a thing that has labels in it. Or vice versa. Anything that has labels in it or has label arguments in it and turn it into a thing that takes strings, and so on. We should be able to take a function that takes a set of string and returns a non-empty list of label and turn that function into a function that takes a set of label and returns a non-empty list of string with no runtime mapping at all. And we can do that if we generalize. We take the list part of that previous signature and just turn it into a type parameter, a higher kind of type parameter. So subst is really interesting. Subst is kind of a way to define type equality without defining type equality. It's kind of a strange function. It's very powerful. It applies to our previous use case. We can just use it with a list, just like we used wrap list. But it does a lot of other things. One of the things it does is define its own inverse. So if you write a function that takes you from f of string to f of label, that just gives you a function that takes f of label to f of string. Not a lot of functions can do that. But there's a good reason that subs can do that, which is that it's proof of type equality. By proof of type equality, I mean that there's no safe way to implement it unless the types are actually equal. If it is possible to write a function with this signature at the top, then those types must be equal. That doesn't mean that we've told Scala C that they're equal. The fact that I've defined subst in my signature and implemented it in my structure does not mean that Scala is suddenly going to know that label equals string. In fact, we have to use it. We have to reveal that fact at only specific points, which are substitutions, hence the name. So in this case, I've cheated to define a monoid for label by just taking the monoid of string and substituting string for label in its type, which is really at runtime just the same monoid, except I've just tweaked its type a little bit, and now I have a monoid of label. But the fact that label equals string was only revealed at the call point of subst. The implementation of monoid of string does not know that label equals string. We don't know now that label equals string now that we've just done this transformation. The only time that that equality appeared was right where we were calling subst. So it's a very confined, constrained way to expose type equality, to let people do pretty much anything they want with your opaque types. It's a very flexible approach. And saying that it's a proof of equality means that its ability to define its own inverse makes a lot more sense. Because if A equals B, then B equals A, right? So in that sense, of course we should be able to write its own inverse with subst, because it's proof of type equality. The problem is that it's proof of type equality. If you are trying to define an abstraction that is enforcing something, you cannot be 100% guaranteed that your enforcement is occurring everywhere. Let's say that you're using this to implement some sort of runtime check on strings before saying that they're labels. For example, Julia Michaels' original use case, which was to check that they're all lowercase and define a type for that. So if we can just arbitrarily substitute in types, we can easily defeat that enforcement, just by making a type that didn't enforce that and then doing subst on it to convert them into lowercase string. So subst is powerful enough to do all of our coercion. But what if we only want to allow some coercions, like ones that are safe, and then forbid the other kinds of coercions? And there are a couple ways to do that. So I'm going to take you down two paths. And depending on the kind of Scala program you're working on, you can decide which path you want to follow. So first, we're going to walk down the object-oriented subtyping path. And we will end in the pit of incoherence. And then we're gonna claw our way back out of that and walk down the functional programming type class-based path to enlightenment. I think you know which path I choose for my programs, but your situation might be different. Incoherence can be pretty exciting in Scala, after all. So if you're writing a program that uses subtyping, this is something we don't do in Scalaz or Scalaz style code. We don't use subtyping because it's broken. But it's there in Scala. There's a good chance a lot of programs depend on it heavily. And you can depend on it too. And you can depend on it in some pretty interesting ways. They might be practically interesting, or in my case, just academically interesting. But I'm going to show you how they work. So one thing that you can do is change your signature to declare a type relationship. So far, the signature has been completely opaque, no bounds. But we can add bounds to the signature. So in these three examples on the slide right now, this structure still declares type label equals string. But this fact is private no matter what we put in the signature. Unless we put label equals string in the signature, of course, in which case, what are we even doing here? You know, go pet the cat. So we can say it's publicly known to all code that label is a subtype of string. We could also say it's publicly known that label is a supertype of string. That doesn't sound that useful, but actually there are some pretty good use cases for it. So it's worth keeping in mind. You can also declare both. They can even be different types. You can say my opaque type is a supertype of some type and a subtype of some other type. It's perfectly valid. These are called translucent because unlike an opaque type, which you don't know anything about, it's invisible. A translucent type, you know something about it. You know that it has some particular upper bound. It's a subtype of string. It's a supertype of string, and so forth.
There are transparent types?
The question was about whether there are transparent types. A type alias would be a transparent type, but you don't. In that case, you don't have an abstraction at all, right? Because anywhere that you wrote in your program label, for example, you could just write string there and your program would mean exactly the same thing. So what are you even doing at that point, right? Like that's just simple type alias usage, which is useful for maybe shortening some of your types that you write down. But it doesn't actually give you any extra layers of abstraction, right? So that would be a transparent type, just a simple type alias. So there's a really big way that this is different from implicit conversions, which is what you might do with any Vowel subclass. And that is that implicit conversions don't compose, but subtyping relationships do. When you declare a subtyping relationship in your signature, you are providing your own value to the great circle of the conformance relation as defined in the Scala specification. So Scala has a ton of rules about what things are subtypes of other types. And when you include one little axiom in it, like labels a supertype of string, anything that can be implied from that will be implied from that. So in this case, I'm using the covariance rule in this example. I'm saying that because string is a subtype of label, therefore list of string is a subtype of list of label, right? So if you use translucent types, you have to be aware that Scala will, at any opportunity, use these rules to imply something that maybe you didn't intend to imply. I'm going to show you an example of that a little bit later, because that is exactly what leads to incoherence. So it's kind of neat, because if you're using subtyping heavily, you can do some pretty crazy stuff that you couldn't just do with classes. So I have a signature here, which defines a bunch of types and a bunch of vowels of those types. Now, a valid structure for this signature could set all 5 of these types equal to string. It could even set all 3 of those vowels equal to the same string. But the user of that module, the rest of the program, would still see all these things as independent and translucent. Wouldn't know anything about the fact that we just threw it all away. So it becomes this sort of big set of pure type level markers that all have declared relationships with each other. Yet underneath, it's all just string and empty string or what have you. So that can come in pretty handy if you are heavily subtyping dependent. The problem with subtyping is that it's subtyping. This is a problem that Julian Michael originally hit when trying to define a translucent new type. His lowercase string was a subtype of string. But if you call reverse on a lowercase string, you're going to get a string back. And that's because you will always get the reverse method that is declared for string. There is no way to change that fact with implicit conversions. Implicit conversions will always lose to methods that are defined directly on your subtyping hierarchy. So you're stuck, right? In the sense of transparency, this actually came up again in that original post. He was asking about how to get it so that those original methods would return lowercase string. But the problem is that in the type system, there's no discrimination between methods on string that will violate that constraint and methods that won't. So there is no way to figure out which things should return lowercase string and which should not. You have to explicitly declare everything if you're going to enforce an ad hoc constraint with your new type, which is one of the common use cases for it. This is one of those implications. If you add an upper bound, it might seem convenient, but you know what? Now you've cut yourself off from a lot of the method namespace. If you don't want this to happen, your only choice is to get rid of translucency. There's no way to fix it with an implicit conversion. It's even worse when we try to bring in type classes. This is a problem that used to exist in Scalaz before we redesigned the new type system. It's that if you define a type class for a subtype that is inconsistent with the type class for that supertype, you have an incoherent type class instance. Because what your behavior is from your type class depends on where you are in the subtyping hierarchy, which can change at any time, right? That is, something that works on a supertype should also work on the subtype. But if we define different type class instances, another common use case for new types, then we get potentially very confusing behavior. So if you define dual of A is a subtype of A, like this, so dual of string is a subtype of string. And we say, well, dual semigroup just reverses the underlying semigroup. Well, if we have two dual of strings, H and W, the result that we get depends on where the widening happens. So if the widening happens after the append, then we get our dual behavior. If the widening happens before the append, and this is very dependent on how exactly method lookup works, then we get the append that we didn't expect, the original string append, right? So unfortunately, another area where you're just going to have to give up translucency if you need this to work consistently. And in fact, that's what we did in Scalaz when we got rid of subtyping for our new types. One of the ways that we can solve this problem is by getting rid of the bounds. But we still want to keep some of the properties of subtyping. We don't want to go back to proving equality, because that might be too powerful for our use case. But we can prove conformance in a very similar indirect way. So just like subst proves equality without taking us all the way back to transparency, this subst_co proves conformance without taking us back to a conformance relation that is seen by the Scala compiler. So this function proves that label is a subtype of string. Also, subst_contra proves that label is a subtype of string. These two are interchangeable. You can define one in terms of the other. You can choose one to be your primitive and define the other in its terms. You can define both of them in the signature and put both of them in the structure. Also valid. Question?
I was wondering, could we also make this more generic and say we want to have both label and string, maybe like one type T and another type S, for example? Could that be done really easily, or do you need separate types for that?
The question was about whether you could abstract out this notion of label and string. Yes, you can.
Okay.
There are 3 different ways I can think of off the top of my head to do that. The simplest one is to just add type parameters. The second one is also to add type parameters, but in a different place. The third one I don't really want to talk about because it's even more confusing. Incidentally, the second one is what is used for Scalaz tags in 7.3. So that's worth checking out if you're interested in that. All right. So I think the way that subst_co and contra each independently prove a subtyping relationship is really interesting because it implies that variance is at the heart of subtyping. A lot of people think of variance as this sort of add-on confusing thing that Scala does. But I've been saying this for at least since last LambdaConf talk I gave 2 years ago that variance is essential. And I think that subst_co and contra show that it's at the very heart of what subtyping means. I'm not the only person to say that, though, and I'll provide you a link at the end. So anyway, I mentioned that we don't like subtyping designs in Scalaz anyway. Well, what alternatives do we have? We can actually take some inspiration from this form, though. So we've gone back to opacity, right? And instead of saying that f must be covariant or f must be contravariant, we say that f must have an instance of the functor type class, or f must have an instance of the contravariant type class. And this means pretty much the same thing that the previous versions of subst_co and contra did. That is, subst_co means that label widens to string in any context where that's safe. And subst_contra also means that label widens to string in any context where that's safe. Just like with the previous ones, you can define either one of them in terms of the other. This is, incidentally, neither of these are showing inverses. Subst_contra is not an inverse of subst_co because the constraints are different. It's more like a contrapositive function. It's a function that means the same thing. It kind of looks backwards, but really it's the same thing. I've just written it in a slightly different way. This is what we want, because unlike with type equality, type conformance is not symmetric. A subtype of B does not imply that B is subtype of A. That would be nonsense. But now that we've introduced type classes like we get from Scalaz, we can start to think about what other kinds of constraints we could use and what that means. And this is where the design field really opens up. Now that we've abandoned the path to coherence, we've climbed out of the pit, we can choose all sorts of different constraints and say, what does it mean if I use this constraint? So functor and contravariant have the meaning I've already said, that label widens to string. What about this one? Well, this says, let's just try to read the signature. If I can fold over f, then I can take f of string to optional f of label So in this case, I've reintroduced validation of labels, right? So for example, I could check that they're all lowercase. The difference between this and a simple traversal where we're checking one string at a time is that I can return the same structure. Sorry, I've been using structure to mean the implementation of a signature. I can return the same value, the same object, just wrapped in a sum. And so we've held on to, even though we're doing validation, we've still held on to a lot of the low cost to zero cost abstraction that we want from this. This is instantly the only way that you can do something like this without, say, a traverse constraint instead of foldable. In a context like this, it's almost like foldable becomes traverse, which is just yet another bit of exotic behavior from defining opaque types. Anyway, we're about to get into something even more complex than that, so if there are any questions about anything so far, I just want to pause and cover those. Yeah?
So, you mentioned you want, I guess, like coercion, which doesn't take any runtime overhead.
Yes.
But I failed to see how in the previous slide where you use functor, you still have to map over the structure.
Okay, the question was about if I take a functor constraint, don't I have to still map over the structure in order to return the new one with the labels inside it, right? The answer is actually you don't. So let's forget about the implementation here. Let's say that I declare in my signature, subsco f is a functor, f of label to f of string, right? And then I implement this in the structure, right? In the structure, label equals string. Therefore, this becomes a function for all f that are functor, f of string to f of string. And I can simply return the argument. The only thing that I'm using the constraint for is to enforce that this is a unidirectional transformation, that I can't use it to prove type equality. Because if I have a functor constraint, I also can't use it to prove type equality, just like with the covariant or contravariant annotations from this version. Does that cover your question? Okay, great. Anything else before we move on? Yeah.
This one might be a little silly because I haven't used them too much, but at one point I encountered this thing known as a Liskov substitution, and I'm wondering, would that work here too, or is that?
The answer was about whether you could use Liskov instead in these cases, and the answer is yes, you can absolutely use Liskov instead. You can use Leibniz as well instead of a standard subst. I like writing them out because it lets you start to refine them when those two things are wrong, which my thesis is kind of that can be very commonly the case, that they're wrong. If they're right, though, you can use them. Absolutely.
It might just be my ignorance, but if a code base has tag types, would it be worthwhile to replace them with opaque types, and why?
The question was about whether it would be worth replacing tag types that you're already using with types defined directly this way. And the reason that you would do that is if the standard subst method didn't quite fit your use case, or you wanted to define multiple types, all of which were known, or you want to write things in a structure that just know that the two types are equal, or that these two types are equal, and these two types are equal, and these two types are equal, in the case of having more than one type. And that can be very convenient to do within a structure, but not so much with tag types. That's a few of the reasons that you'd want to do this. Anyway, I think we're ready to move on. Let's talk about infinite types. A list is an infinite type. It's an optional pair of a head and a tail. So we have either a head and a tail, which is the recursion point, the tail is a list again, or nothing, right? But Scala won't just let you define this as a transparent type alias. It says this error message, illegal cyclic reference. So you have to do something like this case class instead. But now you have an extra layer of runtime overhead. And this is a problem that a lot of people have with using recursion schemes in general, in Scala that you always need one of these layers of overhead. Any vowel is of no help here because it's just not, it's not zero cost enough. It boxes in exactly these kinds of cases. So any vowel subclasses don't help you. You have to have these case class layers. But with opaque types, we can. So first of all, I'll demonstrate that. I defined an opaque type, xlist, and a way to make a normal list into an xlist here. And then I've gone ahead and done it. And when I do that, it looks like what you see at the bottom. Sum of 1, sum of 2, sum of 3, and none. So here's sum of tuple being your cons case, and none being your nil case, compared to the original singly linked list. And Scalaz 8's singly linked list is defined this way. Not precisely, done a little bit more efficiently to avoid having any extra overhead versus standard list. You can go check it out on that pull request right there. So the recursion part makes it tricky though. So far, I've been saying that the structure knows what the underlying type is. But the problem is that the underlying type is recursive. So we still have the case that nothing else can know what the underlying type of xlist is. But now we also have an extra constraint, which makes things much more complicated. That also the structure can't know that the underlying type is recursive. So we want to define a recursive type, but none of our program can know that it's recursive. It just has to be something that you could see as a user of the program. But in actuality, the type checker will never be able to figure out that it's recursive. And we can do that by finally bringing into play the third element, the vowel. The signature and structure have been my focus so far, but now we really need the vowel to play a big role. The vowel here is instance. You'll note that instance now occurs in both the signature and the structure. And that's how we hide the fact that this is recursive. Because when we're defining the structure here, we know as a programmer that this xlist that's being defined within the structure will eventually become instance.xlist. But at the point at which we are defining the structure, it is not known yet. So the fact that instance.xlist occurs on the right-hand side of type xlist is not a recursive type, as far as Scala C can tell. It's just a normal type. So even within the structure, we can use that existential, that type parameter. And that's how we can accomplish our infinitely recursive type. So every occurrence here of instance dot is absolutely essential. What's going to happen is that you'll notice in the signature some of these xlists do not have instance dot before them, and some of them do. And that's going to remain true. There's going to be this distinction until we finally get to the point of using this. So the user of instance, the user of our abstraction, is going to see all these xlists as the same, instance.xlist. But none of our definition will know that. So everyone knows precisely what they need to know in order to actually use this abstraction. So you can't really copy this like I showed earlier with the original label module instance, because it's so dependent on the vowel. We're completing a circle here. The structure implements the signature. We take the structure and assign it to the vowel. And now we're saying the vowel itself has to occur within the signature as well. So everything has to be kind of tied together. And this is how it works. And this is why you have to ascribe all of your vowels. So we create the structure. It knows something about the right-hand side. It knows that its option. It knows that it has an occurrence of instance.xlist within it. But it doesn't know that its own xlist is going to become instance.xlist. So we go ahead and we infer the type of the structure, which still has that information about what xlist is. But then we use this description to widen it, and we throw away what xlist is equal to. And once we've done that, we can take our widened structure and finally assign it to the val, at which point the structure's xlist becomes instance.xlist. Now, if this happened earlier, then we would have an infinitely recursive type. But we threw away the information that would mess us up right before it would mess us up. And now everything comes together. Our structure's xlist becomes instance.xlist. All is well with the world. So, any questions about how this works? Because I know that was a lot. Yeah.
Where do you use instance.xlist and where do you use xlist?
The question was about where to use instance.xlist and where to use xlist.
In the signature.
As in the signature, sure. So when you're writing transformation, when you're declaring functions in your signature, there are some places where the right-hand side will appear naturally when you're thinking about it. There's somewhere where the right-hand side will appear. So, for example, apply with label module. String, the underline type, naturally appears as the argument to apply, whereas label appears as the return type, right? So anywhere that you would expect the right-hand side to appear, that needs to be an occurrence of instance.xlist. Anywhere that you would expect the opaque type to appear, that needs to be just xlist.
So because xlist is wrapping a recursive xlist, that recursive xlist underneath the xlist is instance.xlist.
Exactly. The question was about saying that the xlist underneath xlist is actually instance.xlist. Absolutely. In terms of rolling and unrolling, what uncons here is doing is unrolling exactly one layer of our abstraction. So we had an instance.xlist from our view, and we turned it into an option of A and another instance.xlist. And so it unwraps exactly one layer of our infinite tower of types. And we have the opposite operation with apply, which is we push down one layer of our infinite tower of types, right? I think you were first.
Would it not be easier to implement that using recursion schemes such as fixed?
The question was about whether this would be easier to implement using recursion schemes. You can use this this is a technique that can be used to implement recursion schemes. And in fact, this is how it's done in Scalaz E8. One of the things about this technique is that folks writing recursion schemes libraries are using this technique to implement recursion schemes, because unlike previous techniques, it's type safe and there's no runtime wrapper layer. You can actually get this if you have an existing fix type or mu type that's been defined using this technique. You can just go ahead and apply it to an option of tuple and get exactly the same runtime shape. So in this case, I'm just trying to show how that technique works, because if you want to go and implement a recursion scheme with this technique, it's going to look exactly the same as what I've just shown you, including all the rules I've said about where instance dot has to appear and where it must not appear. It's the same set of rules for implementing recursion schemes. It's the same interface when you're working with it as well. As a user of the recursion scheme library, you won't see this distinction. It'll always be instance dot fix or whatever you want. You had a question.
What is the companion of xlist? Or maybe even a more general question in that, where would you put something in
The question was about where you would put something to implicitly resolve so that it would be in the implicit scope for xlist. And the answer is, first, you would use at least Scala 2.12.4. Second, there is a rule in the implicit search rules that says you have to search the path. Now, instance is included in the path, and it has a super type, which is XList module. So you can't define a vowels companion, but you can define a companion for XList module. So that is where you would put it.
Oh, right. So the companions of the parent of path.
Exactly. Remember that? You're using that subtyping hierarchy again. Now, it was discovered early on when people started using this that Scala didn't implement this correctly. And that's why you have to use Scala 2.12.4.
Could you just put it on the XList module?
The question was about, could you put it in the XList module? And do you mean like in the companion object?
No, just in the module itself.
You have to import everything from the module to do that.
Yeah. It would not be in the implicit scope if you just put it within the module. So you can define it that way, but then you have to make another implicit somewhere else if you want it to be visible.
And one final question.
Mm-hmm.
Is there any performance impact of that?
The question was about if there's any performance impact of that at compile time.
Because it sounds more complicated than the usual companion search.
The answer is no. I don't think it's all more complicated than the usual companion search. This is the sort of thing that happens for Ken build from all the time. Yeah, it's just search the path. You know, it's always supposed to have been implemented. They just forgot, I guess.
If you want to put typeclass instances somewhere in your before 2.12.4 was it?
Mm-hmm.
You can still do it. There's a technique. You have to add a new type and then use its companion. Anyone want specifics? I guess they can ask me after.
Yeah, if you want specifics about that, you should ask Edmund about that after that. Anyway, just a couple more notes about this that might be on your mind before we close out. Can you do this in Java? Yeah, just put your whole program in a single function. That's fine. Go ahead. I want to warn you about this. People get obsessed about primitives and boxing when they start thinking about this, because it does have some implications there. But then they start to think that's the whole point, that it's about primitives and whether or not you're boxing primitives. It's not the point. The point is to get better abstraction and help from our compiler. That's a side benefit, as far as I'm concerned. The focus is better abstraction. You can worry about primitives and boxing later. You can do this kind of thing. This is an interesting exercise. It's like a different way of doing new types with intersections. This is impossible with regular Scala, but using like opaque types and stuff, you can do this. I don't want to explain how, so go ahead and try that out on your own. There's a sit for opaque types. It's pretty cool. It's going to make a lot of this more convenient for your common cases. But just as with tags, it's going to cover common cases. It's not going to work for more exotic use cases like many of the things I've shown you today. The same thing goes for macro libraries. And it's, again, the same thing for tag libraries like Scalaz or Shapeless. Anyway, that's it. All of those links are really useful. You should read all of them.